Hey guys, I'm going to finish talking about independent and dependent events just a little bit, and then we'll move on to the factorials, combinations, and permutations. Let me see, where am I? Right there. Okay, I wanted to talk about the second page. So let's take a look at this first question, number 8. A green cube and then a blue cube. Hang on just a minute. Sorry, I forgot my notes. I had to have something to write on. A green cube and a blue cube are chosen at random with replacement. So we got a green cube and then a blue cube. So let's see, the bag contains 12 blue, 12 red, and 20 green. Determine whether the events are independent or dependent and find each probability. First of all, how many cubes are in the bag? 12 red plus 12 blue is 24, plus 20 green, I do believe that's 44 cubes. So with replacement, so we're gonna pick a green cube, we're gonna put it back, and then we're gonna pick a blue cube. Now, since we're putting the first cube back, what happened when the first pick has no bearing on the second pick because we put the cube back. So those are independent events. Now, the probability of a green and then a blue with replacement. Now I'm going to go to my whiteboard. Now remember, we had 44 cubes. Now well, snap, you know what I did? I forgot to, sorry. I forgot to see, let me see, a green and then a blue, but we had 12 blue and 12 red and 20 green. Yeah, I forgot to write down how many we had. Okay, so the probability of reaching in and pulling out a green cube, well, there are 44 cubes, 20 of them are green. So 20 out of 44. Now I put that cube back. Now if I put the cube back, then that means there are still 44 cubes in the bag. What's the probability of me pulling out a blue? Well, there are 12 blue cubes. That's it. See what we can simplify. Well, I can simplify a lot here. Let's look at that 20 over 44. If I divide both of those by 4, what am I get? Divide by 4, divide by 4. I can divide by 4 here as well. Divide by 4, divide by 4. So that's 15 out of, I do believe that's 121. So our chance of drawing a green cube and then putting that back and drawing a blue cube is 15 out of 121. Now let's go and talk about number 12. Now from the video, I hope you learned what a deck of cards looks like if you don't already know. Remember, a deck of cards has 4 suits: hearts, clubs, spades, and diamonds. Hearts and diamonds are red, spades and clubs are black. There's a total of 52 cards. So each diamonds, clubs, hearts, and spades has 13 cards. Each suit has an ace and a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a jack, a king, and a queen. The jack, king, and queen are called face cards because they have faces on them. Now, if this is still bothering you, I want you to Google an image of a standard deck of cards and you can see them. So let's look at number 12. 2 cards are drawn from a standard deck. Find each probability if no replacement occurs. No replacement. I want to draw a heart, and then I want to draw another heart. Now we're going to look at the other one, an ace and a king. Okay, the probability of drawing a heart. Well, I have 52 cards in the deck. 13 of them are hearts. So the probability of me reaching into a deck of cards and pulling out a heart is 13 out of 52. Now, I do not replace that card, and I reach in and draw another card. Well, if I don't replace the card, then the number of cards in the deck has shrunk by 1. And if I've already drawn out 1 heart, then the number of hearts has also shrunk by 1, so I would only have 12 hearts. So you're going to multiply those together, and that would be the probability of getting 1 heart, not putting it back, and then drawing another heart. I'm going to simplify these first, though. I know that 13 goes into 13 once, and 13 goes into 52 4 times. I know that 4 goes into 4 once, and 4 goes into 12 3 times. The 3 goes into 51. Let me see, 1 17 times, so that's 1 and 17. So that will simplify to 1 over 17. So I have a 1 over 17, a 1 out of 17 chance of drawing a heart, not putting it back, and drawing another heart. Let's talk about drawing an ace and then a king with no replacement. There are 4 aces, an ace of diamonds, an ace of spades, an ace of hearts, and an ace of clubs. So out of those 52 cards, there are 4 aces. I am just checking to see, give me just a second. Yeah, I was afraid I wasn't recording because the last time, I've done this video once already today, and it recorded 2 seconds and then it quit. So all of a sudden I thought, oh my gosh, I forgot to record, but I didn't. So I have 4 chances in 52 of drawing an ace. I don't put that back, so I have 51 cards left. Now, what's the chance of me reaching in and getting a king? Well, if I drew an ace out, I still have 4 kings in the deck. So I still have 4 chances, but out of only 51 cards because I didn't put the first card back. Multiply this out and simplify, or I can simplify first. I know 4 goes into 52 13 times. So that's going to be 1 times 4 is 4 over. I'm grabbing my phone to get my calculator. 13 times 51. Whoops. Help if you could type things in right. 13 times 51 is 663. So I have, what's that? I have 4 chances in 663 of drawing an ace, not putting it back, and then drawing a king. The thing that I want you to remember, if you do replace, then the number of things in the bag or in the deck does not change. So that's going to be independent. If you don't replace, then the number of things in the bag or in the deck does change. Those are going to be dependent. Now let's go and talk about your factorials and combinations and permutations. Now I'm going to pause this recording for just a minute. Let me see. No, I'm not. Never mind. There's something I was thinking about. That's a permutation. Okay. When you see, number 1, when you see 4 with an exclamation point behind it, that does not mean 4. Now that's a whole lot more effective in class, but when you see 4 with an exclamation mark behind it, it means 4 factorial. And what it means is 4 times 3 times 2 times 1. Just multiply it out. Number 2, 6 factorial just means 6 times 5 times 4 times 3 times 2 times 1. That's all it means. Now number 3, 0 factorial. 0 factorial by definition is 1. And I'm going to show you when we go to a whiteboard why that is so. And I also want to show you about 5 factorial over 3 factorial. We're going to work a couple problems like that. Oops. So I will go back to my whiteboard. Now, first of all, let's talk about the 5 factorial over 3 factorial. Well, you know that 5 factorial is 5 times 4 times 3 times 2 times 1. And you know 3 factorial is 3 times 2 times 1. Well, you see the 3's factor out, the 2's factor out, the 1's factor out, so I'm left with 5 times 4 is 20. Now, the guy who did the video showed you a shortcut, but I don't think he explained it very well. So I want to talk about that with you myself. 5 factorial over 3 factorial. Here's what he said. He said just write this as 5 times 4 times 3 factorial, instead of writing 5 times 4 times 3 times 2 times 1. Because if you'll notice down here, we have a 3 factorial, which is 3 times 2 times 1. Those will factor out. And that's when I factored out the 3 times 2 times 1 on the last screen that you saw. You notice I still get 20. Now let's try another one like that. What if I have 6 factorial over 3 factorial? Notice I got a 3 factorial on the bottom. I can write this as 6 times 5 times 4. Now I can write this as times 3 times 2 times 1. If you want to do that, that is just hunky-dory. Over 3 times 2 times 1. Notice the 3's and the 2's and the 1's factor out. I'm left with 6 times 5 times 4. 6 times 5 is 30 times 4 is 120. Or I can do it like this. That's 6 times 5 times 4 times 3 factorial divided by 3 factorial. And the 3 factorials factor out. Doing it the second way just saves you some writing. 6 times 5 times 4 is 120. Now let's talk about 0 factorial. Now by definition, 0 factorial is 1. Why? I'll show you. If I write 4 factorial, I'm going to try to write small and neat. I'm not sure if that's possible on this. That's 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is 1. So 0 factorial is, Now 4 times 3 times 2 times 1, that's 24. So 4 factorial is 24. 3 factorial is 3 times 2 times 1. 2 factorial is 2. 1 factorial is 1. Now let's talk about how we get from, oh snap, where'd it go? How do we get from here to here? Here to here. Well, we divided by 4. Notice we took 4 out. How do we get from here to here? Well, you see how we're missing that 3. So we divided by 3. Well, that makes sense. 6 divided by 3 is 2. What about from here to here? Well, we divided by 2. Well, from here to here, we divided by 2, didn't we? Now, how do we get from here to here? Well, look at the pattern. We divide by 4, divide by 3, divide by 2. So it ought to make sense that we divide by 1. So what's 2 divided by 1? 1. Oh! 0 factorial is 1. Dun, 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 dun. Isn't that cool? 0 factorial is 1. Okay, let's talk about the P's and the C's. So let's talk about number 6, which is 6P4. Let me see. Let me write that one down. 6P4. We'll look at number 7. Number 7 is 7P3. Now, number 5 and number 6, you're supposed to do the formula. Number 7 and number 8, use the calculator. If you don't know how to use the calculator, FaceTime me or Zoom me, and I'll show you how to use the calculator. So we're going to go back to whiteboard. Clear that whiteboard. 6P4. Now, the way I think about these is I call that 6 pick 4. Now, the P is important. Let me give you an example for 6P4. Let's say that we are starting a new club, and right now we only have 6 members. But we still need to pick officers: a president, a vice president, a secretary, and a treasurer. Now, how many different people could be the president? 6. So I got 6 people in the group. How many people could be the vice president? Well, whoever's president can't be the vice president. So I only have 5 people who could be the vice president. Who could be the secretary? Well, whoever's the president and whoever's the vice president can't be the secretary. So I only have 4 choices left. And in the same idea, I only have 3 choices left for treasurer. Multiply these numbers together. That's the number of ways I could pick a set of 4 officers out of those 6 people. 6 times 5 is what, 30? 30 times 4 is 120. And 120 times 3 is 360. Now that may blow your mind a little bit, but there are 360 ways that given 6 people, you can pick officers. Now what I need you to understand is the order of officers matters. It is a totally different set of officers if Levi gets picked to be president than if Levi gets picked to be secretary. So he can be in the group, but if he is in a different position, that's a different arrangement. So when we have a situation like this, and I just call this the president situation, president P matches the P here. Order matters. Order matters. Kentha being the president is different from Kentha being the vice president. The order matters. Now, so let's talk about that little formula that you learned in the video. The formula that you learned in the video for a permutation is n factorial over n minus r factorial. This is n and this is r. So the n factorial, that's going to be 6 factorial divided by 6 minus 4 factorial. So that's going to be 6 factorial divided by 2 factorial. Now I need some more room, so I'm going to have to erase a little bit. Let's see if I can do this. That's slow. I don't like that, but okay. So 6 factorial would be 6 times 5 times 4 times 3. Now I can write times 2 times 1, or I can write times 2 factorial because I have a 2 factorial in the denominator. Those would factor out, and look what I've got left. I got the same thing as I've got here. Folks, I'm just going to tell you personally, when I do a permutation, I do it like this. I don't worry about the formula. If the order matters, you don't have to worry about the formula. You can just do a setup like I just did here, where you can do the formula. It's totally fine. Now let's just do a different example. Let's suppose that your organization grew. And let's suppose now you got 30 members, but you still need to pick 4 officers. So order matters because Allison being the president and Tori being the vice president is different from Tori being the president and Allison being the vice president. If the order matters, use a permutation. President, permutation. How many people do I have who could be the president? 30. How many people do I have who could be the vice president? Well, whoever's the president can't be the vice president, so I have 29 left. How many for secretary? I'd have 28. And how many for treasurer? I would have 27. Or you can use the formula. And the formula says a permutation of 30, pick 4. So it'd be n factorial over n minus r factorial. Now that's 30 factorial divided by 26 factorial. So that's going to be 30 times 29 times 28 times 27. Now notice I got a 26 factorial in the denominator, so I can stop right there instead of writing down 26 times 25 times 24 times 23, because that would take a long, long time. 26 factorial. Those factor out, and notice what I'm left with right there. Now let's talk about a combination. Combinations and permutations are different. Let's clear this out. Let's talk about a combination. Now, I'm just going to pick 3 of you from class. So let's pick Corbin, let's pick Sarah, and let's pick Gavin. I needed 3 different initials, Corbin, Sarah, and Gavin. I need one more, different initial, Jocelyn. Now, out of those 4 people, I need a committee of 2, just 2. So let's think about who I could have. Well, I could have Corbin and Sarah, or I could have Corbin and Gavin, or I could have Corbin and Jocelyn, or I could have Sarah. Now, if I have Sarah and Corbin, that's the same as having Corbin and Sarah, right? Those are the same because it's a committee. They don't hold specific offices. It's just a group of 2. So Sarah and Corbin would be the same as this one. So I don't want to write that down twice. So I could have Sarah and Gavin. I could have Sarah and Jocelyn. I could have Gavin. If I have Gavin and Corbin, well, I've already got Corbin and Gavin. Again, it's a committee, so the order doesn't matter. Corbin and Gavin, Gavin and Corbin, it's the same group of 2 people. So I could have Gavin and Jocelyn. Now, let's talk about Jocelyn. Well, Jocelyn's already been paired with all 3 of the others. So I don't have any more to write down. Those are my only 6 options to pick a group of 2 from a set of 4. Now here, order doesn't matter. When order doesn't matter, when Corbin and Sarah is the same pair as Sarah and Corbin, use a combination. When those are the same, you use a combination. And that would be a combination of 4 people chosen 2 at a time. And the formula for that is going to be n factorial over n minus r factorial times r factorial. Now, this piece is different from the permutation one. What this does is it divides out those duplicates. Like this, if I had written down Sarah and Corbin, you know, my husband's got a cousin named Sarah Corbin. Oh, anyway. Yeah, that meant nothing. But what that r factorial does is it divides out those duplicates. So this is going to give me, I've got 4, so 4 factorial, and I'm choosing 2 at a time. So 4 minus 2 factorial times 2 factorial. Now let's get a little room. Well, 4, that's 4 factorial divided by 2 factorial times 2 factorial. I'm just going to write this one out because the numbers are small. Well, darn it. Just a minute.
You can do it.
There's the 2 times 1. Now 2 goes into 4 twice. So what am I left with? 2 times 3 on the top and 1 on the bottom. That's 6 over 1, which is 6. And that's the same number that I got right here. So when the order does not matter, you're going to use a combination, okay? Order does not matter. I need to show you something. Somebody just crawled up on the counter beside me.
Oh, can they see it?
Oh, yes. Oh, I promise he doesn't really get embarrassed, but I guess he just did. Honey sort of adopted us. He's a stray, and he just showed up, and he looked really sad. He had an eye infection. We started feeding him, of course, and he has adopted us, and we love him. He's a great cat. So we took him to the vet and got him eye drops and all that stuff. Anyway, so now we have this new cat. Name is Honey. This morning he jumped on top of the refrigerator. Now, not from the floor, not from the floor, but jumped on the counter and ended up on the top of the refrigerator. So he's a little weird, but we love him.
He's so cute.
Okay. Now my daughter says he's the best. Okay. Let's talk about, let's just talk about these first 2 questions here, number 13 and number 14. Sorry, number 13 and number 15. There are 50 applicants for 4 jobs. And I'm writing this down. 50 applicants for 4 jobs. And the jobs are computer programmer, software tester, manager, and systems engineer. Find the number of possibilities that those 50 people can fill those 4 jobs. And then the second question is 5 out of 15 students will ride in a car instead of in the van. Okay, now we'll go back to the whiteboard. Oops, don't want to do that. We had 50 jobs, or excuse me, 50 applicants and 4 different jobs. A computer programmer, a systems tester, I think that's what that stood for. What did the M stand for? I forget. And then a manager and a systems engineer. Now the question is it a permutation or is it a combination? If Hayden takes the position of computer programmer, is that the same as if he takes the position of software engineer? No, those are different. Order matters, and when order matters, you use a permutation. So I'm going to have a permutation of 50 taken 4 at a time. Now remember, when you have a permutation, you don't have to use the formula. You can just say, okay, I got 4 positions to fill. How many people could be the computer programmer? 50. How many could be the systems tester? And I'm making that up. I think that's what it was. Well, whoever was the computer programmer can't be the systems tester. So 49. And I'd have 48 for the 3rd job, and I'd have 47 for the 4th job. Multiply that out, and you get a really big number. But that is the total number of different ways that 50 people can fill these 4 positions. If you use the formula, it would be 50 factorial divided by 50 minus 4 factorial. Now look at this, it'd be 50 times 49 times 48 times 47 times, and the bottom's going to be 46 factorial. So I'll stop with 46 factorial. Oops, didn't mean to do that. Sorry. Well, I don't know why that scooted over. Anyway, the 46 factorials will factor out, so I'd have this 50 times 49 times 48 times 47, which is what I've got there. Now, last one we're going to look at. Let's clear all this out. We had 15 students. 5 of them are going to ride in the car instead of the van. Now, if I'm going to take those 15 students and I'm going to pick 5 of them. So it's going to be 15 and I'm going to pick 5 of them. Is it going to be a combination or a permutation? Does the order matter? If I pick, let's see, if I pick Andrew and I pick Jonah and I pick Jordan Cook and I pick, I need some different letters. I pick Trey, and I pick, let's see, Alex. Yeah, I've got 2 J's, but they'll be all right. I've got 2 A's too, don't I? Oh, well. Does the order matter? Now, we're not worried about who sits in the front seat of the car and who sits in the back seat. That's irrelevant. I just need 5 students to go get in the car. The order is not going to matter. So if the order does not matter, it's like picking a committee. If order does matter, it's like picking a president. So if it's like picking a committee where the order does not matter, and it's a combination, you see, committee, combination. If the order matters, that's like a president. So you're going to use P for permutation. So in this case, your formula is going to be what? N factorial over N minus R factorial times R factorial. And remember, that's going to take out the duplicates. Work that out. So that's what, 15 factorial over 10 factorial times 5 factorial. You can work that out and that'll get you your answer. Now, I hope this helps some. If it doesn't help, let me know and we can Zoom or FaceTime one-on-one. So that's all I have to say. And I hope that this has helped you. See you later.
Did you see the